Okay, so welcome back to particle physics and the Standard Model. This is lecture 14. All right. So last time, as you can see here, we dealt with rotations of spinors in real space, right? And here by spinors we mean representations of spin half states using the kit notation or more usefully matrix notation, right? 2 column spinors, sorry, 2 row single column spinors. Okay. So now let us generalize this a bit, all right. So what is, so we just saw what we wrote, we expanded what the rotation matrix was for spinors this way, right. So either using that or just by guessing using the properties of polymatrices, you should be able to tell me what this is. What is UU dagger? What is a dagger? It is a Hermitian conjugate, right. You take the complex conjugate of all the elements and then take the transpose, correct. So a dagger is what? A star transpose, correct. So alright, so if you do this, what do you get for UU dagger? You get the identity, right, and you will find that that is also true for U dagger U, correct. Now what are such matrices called if UU dagger is identity? Some of you might know this, these are called unitary matrices, is not that right? Good. So we have been dealing with unitary matrices, right, that must have been obvious, that is how, so the you generate unitary matrices using the polymatrices, correct. And here is one more thing about this particular unitary matrix. You can see this from either this form or from this form, but I again encourage you to pause the video and work this out. What is the determinant of the U matrix? You will find that the determinant is nothing but 1, okay. So this makes it not just a unitary matrix, it is a special unitary matrix, right, and I am now using the word special not just as an English word, but it is a technical term here. This is literally a special unitary matrix, okay. In other words, the set of U of thetas, right, or the set of all the U of thetas that you can write down using this expansion, right, constitutes something called a group, okay. That set is a group, okay, but group is also a technical term and that group is called SU2 in this case, where S literally stands for special. So this is a special unitary group of dimension 2, okay, good. So now that brings me to some of the juice, some of the meat of this course, namely groups, alright. So without some mastery of group theory, this course will be very difficult to follow from this point onwards, okay. But do not worry, I am going to give you an introduction right here and then I highly encourage you to revise this and go look at Griffiths, Matt Schwartz and other books, okay. So what are groups? These are mathematical entities that are defined by the properties of their symmetry operations, okay, acting on the elements of this group, okay, like matrices, like spinors that we just saw, right. So, what are some symmetry operations? We have been seeing this from the beginning of the course, right. For example, rotations, which can act on group elements like spinors, vectors, even scalars and so on, right. And then inversions. What inversions have we seen? We saw P, T and so on, right. Okay. Operations such as these, right. So, what are these properties? Okay. It is not very hard at all. You would have seen this in high school or even before, but in other contexts, but here we are formalizing the definition for a group. Okay. Number 1, if there exists, that is the symbol for there exists, right. If there exists an Rk element such that you can write Rk as Ri times Rj, okay. Of course, if Ri and Rj belong to the set, are in the set. If Ri and Rj are in the set, and if there exists another Rk, another element such that I can write Rk as a product of Ri and Rj, right. This is one of the properties that I have. What is this property called? It is called closure. All elements need to be written this way, right. Good. Another important property, if there exists some element I, right, such that I always have I times Ri equal to Ri times I equal to just Ri, okay, as part of this set, then that also qualifies as a group if you have this property also. So, what is this property called? Identity, right. Is not this familiar from your very first lessons on addition in school all those years ago, right. So, we will see soon that one subset of addition does form a group, okay. Think about which subset exactly. Not all additions form a group. There is one special form of addition that forms a group, okay. Here is another property that you need. If there exists an element that I am going to call the inverse of Ri such that Ri times Ri inverse equals Ri inverse times Ri gives me what? The identity. Good. So, what is this property called? I just said it, inverse. If you can't form an inverse in a group, then in a set, then that set does not qualify to be a group in the mathematical sense, okay. And finally, this is the final property that you need for it to be called a group. if I take 3 elements and then I combine 2 elements this way and then I obtain a product of that combination with some Ri, if that turns out to be equal to the product written this way where I combine Ri and Rj and take the product with Rk, if these two are equal, then that is another property that makes this set qualify as a group. What is this property called? Associativity. Correct? Very good. That is all that is required to define a group. As long as you have a set, okay, this could be made of infinite number of elements, finite number of elements, does not matter. As long as you have closure, identity, inverse and associativity, if these 4 are satisfied, you have a group. Okay? That is the basic and only definition of a group as such, right. Now, there is something you might have expected, but I did not write down. There is some property that you know of, right. In addition, in multiplication, what did I not write down? I did not write down commutativity, correct. I did not say that I need RiRj to be RjRi, correct. That is because it is not part of the definition, it is not actually. Okay? You do not have to commute, that is one of the beauties of groups, and that is what leads to a lot of very rich physical phenomena that we will see in the standard model, alright. But if elements of the group do commute, what is this group called? Have you heard of this name? It is called an abelian group. Okay, named after the mathematician Abel, right. Notice that although his name is spelled with a capital A, the group that is named after him is still spelled with a small a, right. So, that is how commonplace the name has become, the abelian group's name, alright. So, we just mentioned that the number of elements in the group could be infinite or finite, right. That naturally lends itself to a certain classification of groups, and I can just call them finite groups and infinite groups, correct. Can you think of a finite group? Have you seen any finite group already? Obviously, the operation of parity could form a finite group, correct. You just need psi to go to minus psi, if you, for instance, and then the minus psi will come back to psi, right. So, you just have 2 elements in this case, correct. And what about rotations around a triangle, an equilateral triangle in particular? That is also a finite group, right. As long as I rotate by 120 degrees, I recover the equilateral triangle that I just drew, correct. So, this is called simply a triangle group, okay. So, you can construct any number of finite groups. I can have rotations by 360 degrees over n, some n, and that group would be called a Zn group, right. So, basically parity is what then in this notation? It is a Z2 group, the triangle group is a Z3 group, right, if I set n to 3 or 2, and I can generalize this to any n, right. That is one example. On the contrary, I can also have, on the other hand, I can have infinite groups with infinite elements in them, right. What is a very simple example? We just mentioned it as I was writing down the properties. Addition, but not just any addition, right. Addition of or among integers, correct, right, you can see that, right. So, there is obviously closure and then the identity is 0 here. So, it is not, so here I am taking products, but now addition takes the place of multiplication that I have written here, right. So, if I add by 0 I get the same number, the inverse is basically the minus of that number, and obviously I have associativity, correct. I also have commutativity, but I do not care about that as far as the definition of group is concerned, correct. And since there are infinite number of integers, this forms an infinite group, right. Notice that both of these above are discrete groups. What is discrete about this? Unlike the spinors that we saw just now, these are not living on some continuous space, right. Integers are not continuous on the number line. The Zn by definition these are finite operations, sorry, these are discrete operations, correct. In other words, for discrete groups the elements can be labeled. You can call these A, B, C, D, alpha, beta, gamma, 1, 2, 3 or whatever, right. So, for example, we have already done it here for the triangle group, we can label them with integers for instance, correct. But if something is living on a continuous space, you can't just label them, right. There are infinite number of them, so you can't label it, right. Of course, one thing should be obvious from this: all finite groups are discrete. Yes, necessarily it means you will be able to label them, but obviously not the other way around, not vice versa. You just saw a counter example. Addition among integers is a discrete group, but it is an infinite group. So, not all discrete groups are finite, but all finite groups are discrete. Okay, excellent. Now, since I talked about discrete group, let me just write down the other one in the classification: continuous groups. It just means the elements live on some continuous space, but another way to say it is that elements depend on some continuous parameter. What does that mean? I can use some continuous parameter like an angle or something and generate all the elements of the group. So, if I take an angle and then use that angle to rotate around a vector, I get all, I can basically fill out real space with all the vectors possible, right, as far as rotation is concerned. So, that sort of a thing. Okay. So, these are some abstract notions on groups. Let us look at the kinds of groups that really nature seems to pick again and again to write down the quantum field theory of the universe that shows up as the standard model so far. Okay. These are groups formulated by matrices. We just saw one, the U that was required for spinor rotation, right. So, there is a way to actually deal with these groups in an abstract way also, but if you can formulate them with matrices, why not use them, because we know how to manipulate matrices, right. So, it just makes life easier, correct. So, we already saw one in the case of spinors, but even in the case of vectors we have as examples the rotation group, what else, the Lorentz group, correct, accounting for boosts and so on and so forth, okay, best visualized as matrices. Okay, so let us list some of these, okay, beginning with something that we already saw. So, a very common group is the one consisting of unitary matrices that I am going to label with an N. So, what does it stand for? This is the set of all unitary matrices with dimensions n by n. Again, what are unitary matrices? It just means U dagger the same as U plus 1. Okay. So, that is literally the name of the group, it turns out. It is called the U of, you know, UN, people just say UN, not U of n, UN group, alright. Now, there is a sub case of this, okay. If the let me probably start numbering these, okay. So, let us call this 1, a second group would be if the determinant of these unitary matrices forming the elements of the group is 1, again we just saw an example of this, correct. This group is an, it is just called an SUN group, special unitary matrix with determinant 1. It has certain special properties that the regular unitary group does not enjoy. Not just the determinant, there are consequences to this, there are physical consequences to having SUN as opposed to UN. Okay. Now, suppose the elements of U were real numbers, not complex numbers. Suppose it is a real unitary group. What is this called? These would become orthogonal matrices, correct. Right. What are orthogonal matrices? Literally you just take the dagger here and then now the star with the complex conjugate represented with the star superscript would be the same as what you began with, right. That would mean that I just take the transpose of these matrices that I am representing with O because it is orthogonal, and that gives me identity, right. So, what shall we name this group? We can just call it the ON group. set of all orthogonal matrices of dimension n cross n, right. Okay, this still does not say anything about the determinant, right. By the way, notice that if I were to take the determinant of UU dagger, right, what is the determinant of UU dagger from here? That is just 1, right. That still does not tell me what the determinant of just U is, correct. Correct. So, it could be 1, but it could be any face, right. It could be -1, it could basically pick up a face, correct. So, that is why we specifically focus on one particular case, which is the determinant being equal to exactly 1, right. So, that is why we distinguish this case from the others, alright, because it is not a generic property, good. Similarly here, if the determinant of the orthogonal matrix happens to be 1, then by the same token that group is called just SON, special orthogonal group, alright. Have we seen any SO group before? Are we familiar with the SO group from somewhere? Have we seen in particular the SO3 group? We have, even if we have not seen it under that name, the SO3 group, right, with 3 by 3 orthogonal matrices is exactly what captures the rotational symmetry of any system that has rotational symmetry, right. So, like gravity and so on. So, in particular on cosmic scales, it captures the rotational symmetry of the 3D world that we, 3-dimensional world we occupy, right. So, we saw electromagnetism, Newton's potential and so on, they all enjoy rotational symmetry, right, in 3 dimensions. So, if you were to represent this with matrix operators, then you take matrices from the, you will take elements from the SO3 group, okay, that is what it means. And obviously, just to complete this thought, this would mean angular momentum is conserved according to Noether's theorem, right. So, one fun little thing is that this SO3 is what you would use to rotate in 3 dimensions on vectors, 3 vectors, okay. But then just in the previous lecture we saw that we took 2 by 2 unitary matrices, in particular matrices that are elements of the SU2 group, to perform rotations on spinors, correct. So, that hints at some relation between this SU3, which acts on vectors, and the SU2, which acts on spinors, correct. Although remember, this is made of real elements and this is made up of complex numbers, correct. Nevertheless, although these two groups are distinct, there is something common among them, right. They both act on 3 dimensions, for instance, right. So, hold on to this thought, we will revisit it, okay. There are things called groups that are isomorphic to each other, and there are situations where you can substitute one with the other and make calculations easier and so on, okay. So, groups, these different groups are distinct, but they do have some intricate relations among each other. Okay. So, in the last couple of minutes or so, let me introduce you to the notion of representations of groups. Okay. What I am trying to say here is that these groups can exist in their own abstract space. Okay. So, U of n, SUN and so on, they are all abstract notions which we already formulated using matrices. However, you do not need one particular set of matrices to represent them. Okay. You can use multiple sorts of matrices. So, let me write multiple matrix kinds to represent the same group. Alright. Said differently, if I let me give an example that might probably explain this better. So, if I had an SU2 group, right, we saw that we could have we were using 2 by 2 matrices, right, to write down unitary matrices in the SU2 group that were acting on spinors, correct. But that is just one representation, okay, it is just one representation. What we could have also done is to represent this with some 3 by 3 matrix or even 5 by 5. Okay. This is a higher dimensional representation of the same group. Okay, it is completely possible, just think about it. Alright, the same group, as long as the properties of the group are satisfied, right, as long as this property is satisfied, as long as the other definitions are satisfied, you can always represent a group with other higher dimensional representations also. In fact, you can represent it with lower dimensions also. Okay, so I will just leave you with that, and in the next class we will explore exactly this notation, this notion, and we will see what we mean by a fundamental representation, trivial representation, reducible, irreducible and so on. Okay, these are very important concepts that we will need as we go on to construct and deconstruct the standard model. Okay, so I will leave you with that, and in the next class we will see what all these representations mean. We will see that there is a trivial representation, a fundamental representation, higher order representations, higher dimensional representations, and we will see what we mean by reducible representations and irreducible and so on. And these are all important concepts that we will use when we construct and deconstruct the standard model. Okay, so I leave you with that now. See you in next class. Thank you.